Hi guys, so in this video we're going to talk about geometric series. So perhaps you remember that a geometric sequence is a sequence of the form a sub n is equal to a times r to the n minus 1, where that r is what's called the common ratio, and the a is our first term. So remember, this is the common ratio because the property of a geometric sequence is that the ratio of any two terms is always the same. In other words, to get from one term to the next, we're always multiplying by the same number. So a geometric series is just a series that's based on a geometric sequence. So a geometric series is a series of the form n equals 1 to infinity, a r to the n minus 1. So today we're going to kind of use partial sums as well as some limits that we've already seen to try to investigate the convergence and divergence of geometric series. So where do geometric series converge? That is the question that we are trying to answer. So the first thing that we should do is apply the test for divergence. And the test for divergence, remember, it can't tell us convergence, but it will tell us where this thing diverges. So, or at least it'll give us some of the places that it diverges. So the limit as n approaches infinity of a r to the n minus 1. So we're doing the limit as n goes to infinity of the associated sequence. And we've actually seen this limit back when we were doing sequences. We know that this is going to infinity if r is greater than 1. It is going to a if r equals to 1. It's going to 0 if -1 is less than r is less than 1. And it does not exist because it's kind of bouncing back and forth between positives and negatives if r is less than or equal to -1. So what that means is the sequence converges if r equals 1 or if r is between -1 and 1. So in these two middle cases. However, by the test for divergence, the series diverges here because infinity is not 0. The series diverges here because, again, a is not 0. This series diverges here because, again, does not exist is not 0. And so in these three cases, the series diverges by the test for divergence. However, in this one case, the test for divergence fails. So this is really the only interesting case, if -1 is less than r is less than 1. Because in all the other cases, we can just immediately see that this geometric series will diverge. So basically, we're saying convergence or divergence depends entirely on the value of the common ratio, that r, that number that we're always multiplying by to get from one term to the next. Okay, so what's happening in the case where -1 is less than 1 is less than r? What's happening in the case where -1 is less than r is less than 1? Well, at this point, the only way that we've seen to investigate convergence and divergence of series is the test for divergence. And when that fails, we talked about partial sums. So it turns out that the general term for the sequence of partial sums, general term, the sequence of partial sums, of a geometric series is given by S sub n is equal to a times 1 minus r to the n over 1 minus r. In other words, we can actually find the general term for the sequence of partial sums of a geometric series. Now, where does this come from? We're going to look at that in the next video. For now, we're just going to use it to try to figure out what's happening in this case where our r is between -1 and 1. So, remember that a series is doing the same thing as its sequence of partial sums. So if the sequence of partial sums converges, the series converges, and it converges to the same number. If the sequence of partial sums diverges, then the series diverges. So we just have to figure out then what's going on with the sequence of partial sums that has this general term. To determine convergence and divergence of a sequence, we just look at the limit. So we're going to assume here that -1 is less than r is less than 1. And this is an important assumption because in the other cases, we just don't care about what's happening, right? I only care about what's happening in this case. I already know that it diverges in the other cases, but also because I know that therefore the limit as n goes to infinity of r to the n is equal to 0. Okay, so let's look at the limit as n approaches infinity of a times 1 minus r to the n over 1 minus r. Well, because we know that limit as n goes to infinity of r to the n is 0, this is just equal to a times 1 minus 0 over 1 minus r, which is equal to a over 1 minus r. A is a number, r is a number. We know that r doesn't equal 1. We're only looking at what's happening between -1 and 1. So we're not getting division by 0 here. So this is an actual value. So we can therefore say the sequence of partial sums converges to a over 1 minus r in this case. And if the sequence of partial sums converges to a over 1 minus r, then the geometric series also converges to a over 1 minus r. So in other words, in all those other cases, it diverges. But in this case, when we're between -1 and 1, not only does the series converge, but we can conclude that it converges to a over 1 minus r. So let's kind of write that as a theorem. A geometric series sum n equals 1 to infinity, a r to the n minus 1, converges to a over 1 minus r if -1 is less than r is less than 1, and it diverges if r is less than or equal to -1 and r is greater than or equal to 1. So in other words, we can think of this as if the absolute value of r is less than 1. So that's going to stick us between -1 and 1. Or here, the absolute value of r is greater than or equal to 1. So these absolute values are actually a really useful way of looking at this. So this right here tells me convergence and divergence of a geometric series. So now all we have to do is show that that actually is the sequence of partial sums. So we'll do that in another video. And then we'll go through and we'll look at some concrete geometric series in the video after that. So this theorem, you need to know it. All right, see you guys in the next video. Bye.